Today I will talk about measurement-based quantum computation in symmetry-enriched topological phases. So kind of building on from Arnab's talk in 1D, this talk will be all about 2D systems and some new stuff that we can now, or some new systems that we can now treat from the computational MBQC perspective. So first I'll talk about what we call computational order. So I'll explain how you go from sort of the procedure of MBQC and then how that can be generalized to work in phases of matter. Probably a lot of you in the audience know this, but just to make sure we're all on the same page, MBQC, the basic ingredients are you have a many-qubit resource state, you do single-qubit measurements, and out of this you get a quantum computation. For this talk, I'm going to set it up like this. So we've got a 2D system of qubits, just a nice square lattice, and it's living on a cylinder. So you can think periodic boundary conditions in the vertical direction. I mean, this is not the only way to do this, but you can think of MBQC as kind of flowing from left to right in some sense, where we're just, so in this picture, I've got all the arrows pointing up, mean I'm measuring everything in the x basis, all the qubits in the x basis. And what this does is what we call quantum wire, or what David would have called teleportation in his talk a few days ago. To actually do some sort of interesting or useful computation, you need to measure some of the qubits in the bulk in a rotated basis in the xy plane. So you can think of measuring everything on the left side in the x basis to kind of initialize a known state, and then doing some rotated measurements in the bulk to do some logical gates, and then on the right boundary, doing again just measurements in the x basis to read out the results of your computation. And this is a slide that you might recognize from Arnab's talk, but I'll bring it up again for a specific reason. So just to mention that, okay, we're interested in which resource states are good for MBQC. And it turns out that, well, okay, what do I mean by good is that they have a Lie group of gates, and it grows exponentially with system size. So like the best Lie group of gates you can get is SU 2 to the n. If we have something at least close to that, then I would call it good. It turns out that such states, as Arnab mentioned, are incredibly rare in the space of all many-body quantum states. But you can add back in symmetry, and then suddenly they're not so rare. So we're going to study quantum states with symmetry. And another thing to mention is that, okay, so as Arnab also mentioned, the reason that most quantum states are not good for MBQC is because they're too entangled. And in this talk, I'm going to talk about generalizing MBQC from short-range entangled systems to long-range entangled systems, which might seem like it's kind of obvious that it should work, because if you think that entanglement is a proxy for MBQC, but this tells you that you should not necessarily expect that adding more or different entanglement to your already good resource states would necessarily help you do MBQC. In fact, you would kind of expect that it might hurt MBQC, but I'll show you that that's not actually the case. When I say symmetry, just to clarify what type of symmetry I mean, there are kind of two types of symmetry that condensed matter physicists often talk about. There's global symmetry, so where you have like a single site operator tensor product over every site, and that's a symmetry. There's also subsystem symmetry, which is where you have like a rigid subsystem of sites. So say like a line or two lines or a fractal pattern or something like that. And so the symmetries that we find associated with MBQC pretty much all the time are the subsystem symmetries. The states that we usually think about when we're thinking about MBQC, at least the starting point, is stabilizer states. So as probably everyone knows, a stabilizer state is just a quantum state that's highly symmetric, is one way to think of it. It's got like n symmetry equations, and these symmetry equations happen to be made up of Pauli's. One particularly important stabilizer state for MBQC is the cluster state. It has stabilizer generators that look like this, plus all of the translates. Okay, the symmetries that are going to be relevant for MBQC are going to be those that act only by X or the identity in the bulk. And the technical reason for this, which I won't prove, but we're going to want the symmetries to commute locally in the bulk. So not just like overall, but at every site, the on-site representation of each symmetry should commute with every other symmetry. And so you need to pick one Pauli to have in the bulk, and without loss of generality, we pick X. And so you can take your stabilizers and start to push the Zs out of the bulk to find these symmetries. So I'm just taking that local stabilizer generator and canceling some Zs and pushing them out until I find something like this. So this is one of the symmetries of the cluster state. And you can see we've got a pattern of X's in the bulk, but then at the boundaries, we're not restricted. We're allowed to have X's and Zs. The pattern of X's and Zs can also change because we're assuming sort of a translation invariant system. But so the translates of this pattern will also be symmetries, but you'll find different patterns of X's and Zs at the boundary. Okay, so we've talked about the symmetries. Another object that's really important for MBQC is what we call forward cones. So these are also elements of the stabilizer group, but they they commute overall with the symmetries, and they're allowed to anti-commute locally at only one point in the bulk. And they also have to act trivially on the left boundary. And I can construct these from the local stabilizer generator just like I constructed the global symmetry. So I see some Zs and I want to push them now. Instead of to either boundary, I want to push them to the right boundary. So I just start playing the same game and I push my Zs all the way off to the right boundary and I find something like this. And you can see that with respect to the system-wide symmetry, that this anti-commutes at just one point in the bulk, and then it also anti-commutes on the boundary. So overall it commutes. It's an element of the stabilizer group, so we should expect that. And it satisfies all those requirements that I listed earlier. Why we're interested in these forward cone things is that these things give you each one of these gives you one logical rotation for MBQC. And I'll give you a bit of a hand-wavy idea of why that is. I can rewrite this symmetry equation. This stabilizer equation is saying, okay, this is a stabilizer, so I can say that Z acting at this point, if I absorb it, then pops up as this pattern of X's and then something at the boundary. It turns out that, okay, you can kind of, in a hand-wavy way, see that if I do a measurement in the XY plane, which is rotated about the Z axis, so I'm measuring in an eigenbasis that's a superposition of plus state and minus state, or plus state and Z acting on plus state, the Z is going to pop into the stabilizer state, come out as this pattern of X's and Z's, and if you work it out, you'll see that the logical rotation for MBQC is a rotation by this thing that appears at the boundary, so this XZXZX. And okay, so one of these cones gives one rotation. These are all the cones that appear in the 2D cluster state in this example. And so you can see that they end in different ways on the right boundary. And those different ways give us a set of different logical rotations for MBQC. And those logical rotations generate the Lie group of gates that are available for us to do quantum computations. We have a bunch of rotation axes, but one interesting question is, which Lie group do these rotation axes generate? And given some family of stabilizer states, so like the cluster state on increasing system sizes, can we know what the Lie group is as a function of n? For the cluster state, we do know this. It's SO 2 to the n for n even, and SP 2 to the n for n odd. But for other stabilizer states, we don't know this. We can construct this, but we don't always have a proof for it as a function of n. And so that's an interesting problem, not one that I'll talk about in this talk. Okay, and then even more reasons why these forward cone things are interesting for MBQC is because it turns out they're really all you need to do computation. You don't need the exact stabilizer state. You actually just need the expectation values of these things to be non-zero and the state to be symmetry respecting. So as long as those two conditions are met, then your state actually has equivalent computational power as the exact stabilizer state. And so for that reason, we call these the expectation value of the forward cone operators computational order parameters. And this is a plot from 1D from a paper that Robert and Arnab wrote, but this is just showing you that there's a phase transition as you perturb the exact 1D cluster state. In 1D, these forward cones are string order parameters, and so you see a phase transition from the phase that has computational power to a phase that has no computational power in 1D. And the same sort of thing holds in 2D, just with order parameters that are not strings anymore. They're sort of cone-like, or they have some 2D structure. Okay, just to formalize this a bit, this is like, okay, not all the way to formal, but a little bit closer to formal. So the requirements for this computational order, computational phase, is that you have, in 1D, you need a short-range entangled state. It has to be symmetric under a group G that's isomorphic to Z2 to the sum power. And then you need all these string order parameters to be non-zero. Given that, you get the Lie group generated by, here it says, I mean, to be technical, it's a projective representation of G, but what you can just think is the Lie group generated by how the string order parameters terminate on the right boundary. Under those conditions, you can compute using gates from the Lie group generated by the Lie algebra from those Pauli operators. As an example, here's the 1D cluster state. On the left, I have my symmetries. So there's two of them. So I have Z2 cross Z2 is the symmetry group. And then on the right, I have the string order parameters. So they kind of look like symmetries, but they're cut off in the bulk, and they have something sitting there at the end of the string. These are my 1D equivalent of forward cones. I call them R. And the expectation values of these are computational order parameters. And at the right boundary, we see the way that these terminate. They terminate in a projective representation of G. And if you look at the Lie algebra generated by X and Z, of course, it's SU2. So that tells you that you can do, with the 1D cluster state, any 1-qubit rotations. And not just with the 1D cluster state, but with any state that it's invariant under the U's and has expectation value non-zero for the R's. Okay, so now going to 2D, you might expect that it's like something similar. And it basically is. It's almost exactly the same. But the key difference is this line in red here, which is that we no longer require short-range entangled states. So in 2D, you can have different. In 1D, I mean, okay, you can have long-range entangled states, but like, I'll get to this later, actually. But the key line is that you don't need to be short-range entangled. You just need to be related to that reference state, the stabilizer state, by a suitable local finite depth unitary. What I mean by suitable is basically that it kind of has finite spreading when you conjugate local operators by it. Under those conditions, the result is essentially the same. You just replace 1D string order parameters with 2D cone-like operators. And then as long as you have symmetry and non-zero order parameters, you can compute with the Lie group generated by whatever pops up on the right-hand boundary. Yeah, that's basically the summary of how we think about computational order at the moment. And so just to emphasize that the things you need are not, they're derived from a reference stabilizer state, but they're not restricted to just that state. There's some sort of minimal set of objects that we need to compute, and these objects are available throughout phases of matter. And we'll call those phases or those states computationally ordered. And so now that we have a notion of computational order, well, condensed matter physicists are also very interested in phases and classifying states by simple objects. So let's think about how computational order relates to physical order. And so just to review how things stand on the physical order side, there's sort of two classes of quantum many-body states according to condensed matter physicists. There's short-range entangled or topologically trivial states, and there's long-range entangled or topologically ordered states. And you can't create one method of separation is you can't create long-range entangled states from short-range entangled states using finite depth local unitaries. Okay, and when you add symmetry, the game changes a little bit. It's not what states can I connect by finite depth local unitaries. It's what states can I connect by symmetric finite depth local unitaries. So you kind of get a refinement of this classification. And so on the short range entangled side, you get what's called SPT order, symmetry protected topological. And so yeah, those states would all be trivial from the previous point of view, but now some of them are non-trivial because they can't be connected as long as you respect the symmetry. And then on the topologically ordered or the long range entangled side, you get what's called symmetry-enriched topological order, because you already had some interesting stuff going on, but that stuff can have non-trivial interplay with the symmetries that you add. So you can get something even richer than just the standard topological order when you add symmetry. Okay, the question is, we now can talk about computational power as a property of quantum states. So how does this line up with the notions of physical order? And in 1D, we have a really good idea of this. It's just SPT order. SPT order seems to line up exactly with computational order. But in 2D, there's kind of, in 1D, there's really, like, there's only one non-trivial SPT phase in 1D, so it's a very simplified situation. In 2D, there's many more SPT phases, and you also have topological order and SET order. So the picture gets a lot more complicated. It had been shown previous to this work that we could find, as you might expect, computational order in SPT phases in 2D. And all the examples were in SPT ordered systems. But now we can show that you're not limited to SPT in 2D. You can actually go to long-range entangled states, and you'll still need the symmetry, so these will be symmetry-enriched topological states. Okay, so now I've done a bunch of theory and formalism, so I'll go over a couple examples that illustrate how this works in topologically ordered systems. So the first one is an example that's been used a lot, but with a bit of a twist. So it's the toric code with an anisotropic magnetic field. So the standard toric code, you have these are the usual stabilizer generators for the toric code. And then if you want to perturb the toric code, the standard thing to do is add an X magnetic field and a Z magnetic field on every bond. But we're going to only add X magnetic fields on the vertical bonds and Z magnetic fields on the horizontal bonds, so anisotropic. And so you get a Hamiltonian, something like this, stabilizer generators, and then some magnetic field strength for the vertical bonds, and then another one for the horizontal bonds. And what this does in terms of the excitations of the toric code is says that you're not allowed, the magnetic field makes vertical pairs of anyons forbidden. And it also induces a cost for moving anyons vertically. But you're free to move them and create them in the horizontal direction. So what you get is, from the condensed matter perspective, you get a symmetry-enriched topological phase as long as Hz and Hx are below some value. And then as you increase those magnetic fields, you move to a trivial phase, or you condense one of the anyons and confine the other. Okay, when you have this anisotropic magnetic field, you respect a set of subsystem symmetries that look like this. So it's two lines of X's on the vertical bonds, or parallel lines of Z's on the horizontal bonds. We can, sort of like we can detect computational order with string order parameters, we can also detect topological order with string order parameters. These are the string order parameters we use to detect topological order in this toric code model. The expectation value of them is 0 in the toric code state and 1 in the trivial state. So it's kind of flipped from the way that you have the computational order parameters. Computational order parameters are 1 at your perfect reference state and 0 at your computationally trivial state. And then to sort of confirm that we have symmetry-enriched topological order, we can look at how the symmetries interact with the topological order. The topological order is characterized by the anyons that appear in the system. And what you can do is look at relations. So relations are products of symmetries that give you the identity. So in this case, there's two relations. You can kind of take all those parallel rows of X's and wrap them, multiply them together, and they'll give you the identity, and the same with the parallel rows of z's. And then if you truncate a relation to a finite region, you're going to see that that's equivalent to applying an operator around the boundary of that region. And if that operator happens to be an ennion, then that shows that the ennions interact non-trivially with the symmetries. And so in this case, if you sort of think of like truncating those parallel lines to this, to just sort of multiply over this square region, you see that you get a ring of x's around that, and that's the string operator for one of the ennions in the toric code. This SET identification scheme, David Stevens wrote in a paper about it, so he can tell you more if you have extra questions. And okay, so here's what the computational order parameters look like. Similar to the 1D cluster shape, they look a lot like the symmetries, but you've just kind of cut them off at one point in the bulk. And then you kind of have to fix it up at the endpoint with something. And we can see that they terminate at the right-hand side in an XX or a Z. So the Lie algebra generated by XX and Z is the free fermion Lie algebra. So it's polynomially in size, which tells you that the quantum MBQC with this state is classically simulable. So it's not trivial, but it's also not that useful. What is kind of interesting is in the toric code, we can have some like nice exact results about the correspondence between the computational order parameters and the string order parameters. So to do that, I'm going to map this model to a bunch of Ising chains. So you can have one mapping that sends all of your A's to a pair of ZZs on some sort of, on like an Ising chain, and all of your horizontal Z operators to just an X. And similarly, it'll send the B's to a ZZ and these to an X. Because if you look at if you look at adjacent rows, then the operators along a single row don't interact. They all commute with the operators along another row because of the way we've set up the magnetic fields. So what you actually have is a bunch of rows of non-interacting chains. And so you get this Ising Hamiltonian if you do that mapping. You can also, you get two different types of Ising chains. You could also do another mapping that sends the A's to a single X and the magnetic fields to a ZZ term, and same with the B's. And then you would get two, again, Ising chains, but sort of with the couplings reversed. This is related by what's called a Kramers-Wanier duality. So you can relate, this is the duality that like flips the couplings. So it just basically maps X to ZZ and ZZ to X, going from one side of the duality to the other. So these two transformations are Kramers-Wanier dual to each other. And yeah, you take the Kramers-Wanier duality and you can flip between one and the other. We can take advantage of that to show that there's a relationship between the string order parameters and the computational order parameters. So this slide is, a mess, but we only need to focus on the bottom left-hand corner. So I've got the transformation of my string order parameter goes to a string in the Ising chain, a string of x's, and the transformation of the computational order parameter goes to a ZZ. If I do the opposite transformation, then I get the opposite result. The computational order parameter goes to a string of x's, and the topological order parameter goes to a ZZ. And then you can see that these are Kramers-Wanier dual to each other, going across the columns. So like this, if you apply the duality to this one, then you get this one. So this tells us that these are going to respect the exact same phase transition. So in this, like in the case of this model, we can say that exactly the topological phase and the computational phase coincide. And we can confirm that numerically. So remember I said that the order parameters will have flipped values at the endpoints or at the reference states. And that's what you would expect if they're Kramers-Wanier dual to each other. And so we did a tensor network simulation of this, and the top ones are the computational order parameters, and these are the topological string order parameters. And you can see that they cross, and I mean the phase transition would, in the limit of infinite size, appear here, but they cross and they behave exactly as we would expect them to. So everything seems to be working out nicely. It's working out nicely, but we still are, like, this is a nice example where we have lots of analytical tools that we can apply and show a nice correspondence between the two types of order, but it's not computationally universal. As I said, the Lie algebra is only the Lie algebra of free fermions, which is classically simulable. So we have another example which is computationally universal and still topologically ordered, and we call it the XZ star model. The reason for that is because the stabilizers look like kind of like stars made up of X's and Z's. So what you have is like the X stars exist only on the even rows, and the Z stars exist on the odd rows. And now this, okay, so I've changed the visual conventions a bit. So now every square is a qubit, just to make sure we're all on the same page. And we're on a square lattice, not on the vertices of a square lattice, not on the bonds. So a little bit different than the toric code. And okay, so you can derive the subsystem symmetries for this model again. And what you get are these sort of three periodic things. And you can also derive the excitations, so things that anti-commute with the stabilizers only at their endpoints. These are going to create anyons, and you can find that there are 4 types of excitations here. There's an E, an E bar, an M, and an M bar. And if we check how they sort of braid and anti-commute, you can see that the E and M behave like one copy of the toric code, and the E bar and M bar behave like another copy of the toric code, and then they don't interact with each other. So from the topological order side, we would say that this is 2 copies of the toric code. And you can also do an SET analysis with sort of truncating the subsystem symmetries and then looking for those operators that appear around the boundary of a finite region. And you'll find that this has the same symmetry fractionalization pattern as 2 copies of the toric code. So for all the condensed matter tools that we have, this looks like 2 copies of the toric code enriched by subsystem symmetry. But the interesting thing is that this, from a computational perspective, is much, much better than 2 copies of the toric code. So if you just naively put 2 copies of the toric code together, you would expect that classically simulable plus classically simulable equals classically simulable. But that's not the case. You find that because of this sort of weird 3 periodicity of the forward cones, you actually get extra stuff at the right boundary. And these extra rotation axes are enough to take the Lie algebra from being polynomial in size to exponential in size. So you get these ones. So they're like SU2 Ly is the size of the system now, and SU2, almost SU2 to the Ly minus a small constant. So according to my criteria, these would be good resource states or universal resource states for MBQC. And that brings us to the end of the talk. So just to summarize, we now have tools that can go beyond short-range entangled states to apply to lots of the more interesting physical orders that we see in 2D, and we can characterize those systems also from the computational perspective. We have a couple examples. We have the toric code with this anisotropic field, and we can do lots of nice analytical stuff to show that there's some nice relations between the objects we care about for computational order and the objects that we care about for physical order. But that example is not universal for MBQC. So we also have another example that shows that MBQC is fully compatible with SET order. Remember, I said that that's not necessarily what you would expect because of the thing where a lot of states were really too entangled to be useful. But it turns out that somehow the entanglement in topological phases is not damaging to MBQC, at least not always. And we also have this weird phenomena where SET order and computational order don't quite line up. So we're still a bit puzzled about what's the specific precise relationship between these two types of order. Why does it look like you have two copies of the toric code in the XZ star model, but computational order actually tells you you've changed quite a bit from that expectation? So that's the question we're working on understanding now. And with that, I'll end the talk. Thanks for listening.